Greetings, this is Rick Powers coming to you from my home office for Western Technical College. Introductory statistics, example of hypothesis testing. I'm going to share my screen with you so that you can see what I'm doing. So consider this situation. A recent study found that concussions were 11% of the injuries of college students on equestrian teams, horse riding, based on 568 injury. The NCAA reports that 7.4% of all college football injuries were concussions. Is there evidence that the rate of concussions for the population of equestrian teams is higher than the rate for football teams? Use alpha is equal to 0.05. Step number 1, determine the hypotheses. The sample information gives us 11%. We are comparing that to 7.4%, which is not from a sample, but is given as a standard number. So the hypotheses are the null hypothesis, P is equal to 0.074. The alternative hypothesis, P is greater than 0.074. Note the number is the same in both hypotheses. The null hypothesis has an equal sign. The alternative hypothesis shows the direction of the comparison. Note the letter P in these statements represents the population proportion of concussions on equestrian teams. We start by assuming the concussion rate is the same as the standard number from football, and we want to prove that the rate is higher for equestrian teams. Step 2, verify the conditions of the test. We'll skip this part. We're going to assume everything's fine. Step 3, calculate the test statistic or the test value. And step 4, calculate the p-value. These two calculation steps can be done using SALT. Here's the link to SALT. And here is SALT. So I'm going to be going back and forth between the notes and the actual software. Under procedure selection, choose one sample proportion. Procedure selection, one sample proportion. Next, fill in the information from the sample. The number of successes would have the symbol X. The number of trials has the sample N. In our example, N is equal to 568, and the number of successes is a percent of the number of trials. So then X is equal to 0.11 times 56.8, which equals 62.48, which rounds off to 62. In practical terms, there might have been 62 concussions, and the 11% given to us may have been rounded off from 62 divided by 568. Since numbers are always changing in statistics, we will not worry about rounding at this point. So I'm going to fill in the information from the sample. The number of successes is 62, and the number of trials is 568. Make sure the button hypothesis test is clicked. Then the hypothesized proportion is the number from the null hypothesis, which in our example is 7.4% or 0.074. Hypothesized proportion, 0.074. Indicate the direction of the alternative hypothesis, in this case, greater than. Greater than. Click Generate Results. Generate Results. There we are. Note that SALT gives us the null and alternative hypotheses. The null hypothesis, P is equal to 0.074. This would be that the equestrian population proportion is equal to 0.074. The alternative hypothesis, the equestrian population proportion, is greater than 0.074, greater than what was observed in the football. The Z statistic is the test value. It's a description of how far away our sample number is from what we would expect if the population followed the null hypothesis. For this example, the test value is about 3.2. Z statistics, 3.2. The p-value refers to the probability of having an extreme sample based on our sample information. It's the area in the tail of the distribution. In this case, the right-tailed area based on a z-score of 3.2. That area is very small, p-value 0.000686. Now, I want to show you what that looks like in terms of a graph by looking at the distribution calculator. If I have a normal distribution and I put in a z-score of 3.2, and I want the right tail, 3.2, positive 3.2, then you see that's a very small area. 3.2 is out here. It's a very small area. Draw a conclusion and interpret the meaning. Since the p-value is less than alpha, we reject the null hypothesis. Therefore, there is enough evidence to prove the alternative hypothesis. Stated in the terms of the problem, with 95% confidence, there is enough evidence to prove that the population proportion of concussions on equestrian teams is higher than the rate on football teams. Note, we have proven the sample number was an unusual event, based on assuming the equestrian rate was the same as football. So it's reasonable to say that the rate of concussions for the equestrian population is higher than football. I'm going to read this again. We've proven the sample number was an unusual event. It's reasonable to say that the equestrian population number is higher than football. Is this important? Does it have practical significance? Well, we don't know. We are not sports science experts. But you could use Google to see articles about concussions for equestrian riders. Wrestling is another sport that also has high concussion rates.